Hello dear students, welcome to mathematics class. In this class, let us discuss the example on Abelian group. So, until the previous class we have proved that the general set means the set of natural numbers, the set of integers, the set of real numbers, they will be the groups under the given binary operation that we have proved. But now here it is a particular group is given, that is G equal to 1, 5, 7, 11 is an Abelian group with respect to the binary operation multiplication modulo 12. So, it is not only multiplication, so it is multiplication modulo 12. So, for this example, first we need to consider a multiplication modulo table, right, and after that we need to satisfy the 5 laws. They are associative law, closure law, identity law, inverse law and commutative law, which are necessary to prove the set is Abelian group. So, now let us construct the multiplication modulo 12 table. So, here let G is equal to 1, 5, 7, 11. So, it is the given set G, and then here the binary operation is multiplication modulo 12. So, it is a symbolic representation of multiplication modulo 12 and the elements 1, 5, 7, 11 and the same elements must be in the column, that is 1, 5, 7, 11. So, therefore, it is the table. Right? This is the multiplication modulo table. Now, first consider the first element in the first column, then multiply this element with each of the elements in the topmost row. So, it is the topmost row. Now, 1 into 1 is equal to 1, then 1 into 5 is equal to 5, 1 into 7 is equal to 7, 1 into 11 is equal to 11. And the next element, that is 5. Now, multiply this 5 with each of the elements. Then 5 into 1 is equal to 5 and 5 into 5. 5 into 5 is equal to 25, but here we should not write 25 because this is not only multiplication, it is multiplication modulo 12. So, therefore, here if the product of two numbers is greater than 12, then we need to divide that by 12 and we need to substitute the remaining remainder. So, therefore, here in the first row we got the element, that is 1, then if you multiply this 1 with each of the 4 elements, the product is not exceeding 12. So, therefore, we have written the product directly. But in the second case or the second element, so the first product is less than 12, no problem, we have written directly. But the second product, that is 5 into 5 becomes 25, then divide that 25 by 12, then put the remainder here. So, after dividing the 25 by 12, the remainder is 1 because 12 2s are 24, then remaining 1 is the remainder. Then 5 into 7, 5 into 7 is equal to 35, then if you divide that by 12, then here 35 dividing by 12, so 12 2s are 24, then remaining remainder is 11. So, therefore, here we need to substitute 11 and 5 into 11, that is equal to 55, then 55 dividing by 12. So, here 12 4s are 48, then remaining 7 is the remainder. So, therefore, this is the procedure to construct a multiplication modulo table. So, whatever the modulo number is given, if the product of two numbers of the given set is greater than 12, then we need to divide by that number and substitute the remainder. If it is less than 12, then we can consider that product directly. Now here 7 into 1 is equal to 7 and 7 into 5 is 35, then the remainder is 11. 7 into 7, that is 49, then if you divide that 49 by 12, then 1 is the remainder. Then 7 into 11, that is 77, then after dividing that 27 by 12, 5 is the remainder. Similarly for the last number, that is 11. So here 11 into 1, that is equal to 11, then 11 into 5, that is 55, dividing by 12, then we got 7 as the remainder, then 11 into 7, that is 77, 5 is the remainder, 11 into 11, that is 121, then 1 is the remainder. So therefore here we have constructed the multiplication modulo 12 table. Then according to this table, we need to write down the all 5 laws. So for the previous examples, we are used to write the laws by considering the general elements of the given set, for example A, B, C, like that. But here particular numbers are given, then and also the binary operation is multiplication modulo 12. So therefore here there is a small change in writing the properties. So first one, that is closure law. Closure law. So according to this table, all the elements of the table, here we have first row, second row, third row and fourth row, and first column, second column, third column and fourth column. So in this table, is there any other element which is not in G? So here G equal to what? 1, 5, 7, 11. If you look at this table, only those elements are repeated, but there is no other element other than 1, 5, 7, 11. Is it right? So therefore here 1, 5, 7, 11, 5, 1, 11, 7, 7, 11, 1, 5, 11, 7, 5, 1. Right? There is no other element other than 1, 5, 7, 11. So therefore if this is the case, then we can say that closure law satisfied for the given binary operation and for given set. So here writing the closure law, the above table contains only the elements of G. So if any other element is existing other than 1, 5, 7, 11, then we can say that closure law is not satisfied, means the binary operation is not closed under the given set. So therefore here all the elements belongs to the given set, that is 1, 5, 7, 11. So therefore we can say that closure law satisfied for the given set G under the binary operation multiplication modulo 12. So here therefore closure law satisfied for G under multiplication modulo 12, right. This is the first law. Then second one is associative law. Associative law. So here we can consider the three elements arbitrarily, then we can verify the law of associativity. So let 1, 5, 7 belongs to G. Let us consider these three elements. Then 1, the binary operation is multiplication modulo 12, then here it is 5 and multiplication modulo 12 and here it is 7, right. So it is equal to it is equal to what? In the first bracket, that is 1 into 5, which is less than 12. So, therefore, we should consider the product directly, that is 5, and here multiplication modulo 12 and 7. Now, 5 into 7, 5 into 7 is 35, then here it is multiplication modulo 12. If the product is greater than 12, we need to divide that by 12 and we should consider the remainder. So, here 5 into 7 equal to 35 and dividing by 12, then 11 is the remainder. So, therefore, its value is equal to 11. Now, it is the LHS of the associative property. So, here the associative property is A star B star C is equal to A star B star C, right. So, here this is the LHS and this one is the RHS. Now, we have verified the value of that multiplication modulo 12 for LHS part. Then for the RHS part, that is 1 multiplication modulo 12 and here it is 5 multiplication modulo 12, 7, right. Here 5 into 7, 5 into 7 equal to 35, then dividing by 12, 11 is the remainder. So, therefore, first element will be as it is 1 multiplication modulo 12 and value of this one 5 into 7, that is 35 dividing by 12, 11 is the remainder. Now, if you multiply 1 and 11, so that becomes 11, right. So, therefore, here LHS and RHS both are equal. So, therefore, it implies that 1 multiplication modulo 12 5, here multiplication modulo 12 7 is equal to 1 multiplication modulo 12 5 multiplication modulo 12 7. So, it is the associative property, here LHS equal to RHS, hence associative law is satisfied for the given set G under the binary operation multiplication modulo 12. And you can verify the same thing for considering the other element, that is 1 5 11 or 5 7 11, whatever the possibilities are there. So, here we can conclude that associative law satisfied for G, associative law satisfied for G. Then next one is identity law, that is the third law, identity law. So, here how to find the identity element? So, if it is simply a multiplication, then one will be the identity element, right, but it is multiplication modulo 12. Then here in this table, so this is the topmost row 1 5 7 11. So, this is the top row and this is the first row, second row, third row and fourth row, right. So, here in these 4 rows, which will be same as the topmost row, then corresponding element to that row will be the identity element, right. So, here 1 5 7 11, 1 5 7 11, these two are one and the same, means topmost row is same as the first row and the corresponding element of the first row is here. This is the corresponding element of the first row. So, therefore, this one will be the identity element of this set. So, here write down the first row is same as topmost row, right. The first row is same as the topmost row and the element 1 is the corresponding element of first row. Therefore, E is equal to 1, the identity element. If the identity element exists, then we can say that identity law satisfied for G. Therefore, identity law satisfied for G. Then fourth one is inverse law. This is the inverse law. Here, to find the inverses of all the elements, we should go on searching the identity element in each row, right. So, here in the first row we have the identity element 1, then in the second row also we have 1, third row also 1, fourth row also 1, means in each row we have the identity element. If there exists identity element in each row, it implies that there exists inverse for each and every element of the given set. Then how to find the inverse of the elements? So, in the first row we have 1 here, it is the 1, and corresponding element of this row is 1, and this is the also 1, means we can say that these two are the inverses of each other, means inverse of 1 is 1. This is for the first element. Next, here in the second row 1 is there, and corresponding to this 1 we should go this direction, that is horizontally and vertically. Horizontally the corresponding element is 5, and vertically also we have 5. Then we can say that inverse of 5 is 5. And in the third row, here it is the 1, then horizontally the element is 7, vertically also 7 is there. So, therefore, inverse of 7 is 7. And in the last row, in both the directions the element is 11. So, therefore, we can say that inverse of 1 is 1, inverse of 5 is 5, inverse of 7 is 7, inverse of 11 is 11, means each of the element of the given set have the inverses. Then it is enough to say that inverse law satisfied for the element, sorry, for the set G. So, it is in this case the inverse of the element is itself, but in the different examples that will not be same, but this is the way to find the inverses of the elements. Now, inverse law in table 1 occurs in every row. In table 1 occurs in every row, because in the first row, second, third and fourth, in all the rows 1 is there. So, therefore, in the table 1 occurs in every row, and hence there exists inverse for each element of G. Therefore, there exists inverse for each element in G, right. So, therefore, already we have find the inverses of the elements. Inverse of 1 equal to 1, inverse of 5 equal to 5, inverse of 7 equal to 7, inverse of 11 is equal to 11, and the fifth one is commutative law. Commutative law. So, here the statement of the commutative property is A star P is equal to B star A, if star is the binary operation. But if the binary operation is multiplication modulo or addition modulo, then here this is something different. So, here look at the first row, that is 1, 5, 7, 11, and the first column, that is also 1, 5, 7, 11, right. So, the first row is same as the first column. Then second row 5, 1, 11, 7. 5, 1, 11, 7. So, it is the second row, and the second column 5, 1, 11, 7. So, therefore, you can say that second row is same as second column. Then the third row 7, 11, 1, 5, here 7, 11, 1, 5. Therefore, third row is same as third column, and fourth row 11, 7, 5, 1, fourth column 11, 7, 5, 1. So, therefore, fourth row and fourth column are one and the same. So, if this is the case, means each row and each columns are one and the same, then we can say that commutative law satisfied for given set G. Means first row should be same as the first column. Means if you consider the first row, then you have to consider the respective column. First column, second row, second column, third row, third column, fourth row, fourth column. If they are equal, then we can say that commutative property is satisfied for the given set. Then here to write this one, each row is same as the corresponding column. Hence, commutative law satisfied. Therefore, the given set G under the binary operation multiplication modulo 12 is an abelian group. So, here it is the example G equal to 1, 5, 7, 11 is the abelian group under the given binary operation, that is multiplication modulo 12. And here one more example is there, that is prove that G is equal to 2, 4, 6, 8 is an abelian group with respect to the binary operation multiplication modulo 10. In the previous example, it was multiplication modulo 12, and here it is multiplication modulo 10. Here we need to multiply the two elements. If their product is less than 10, then consider that product directly. If the product is greater than 10, then we should divide the product by 10, then consider the remainder in the table. So, now we have to solve this example, that G equal to 2, 4, 6, 8 is an abelian group with respect to the binary operation multiplication modulo 10. It is also similar to the previous example only. So, first see the first example carefully and try to solve the second one, that G equal to 2, 4, 6, 8.